So we are going to look at long division. We have done this with numbers. So I'm going to start with numbers so that you can see the relationship between what we did probably in middle school, primary school, on dividing numbers, and how we can take that and apply to rational fractions or rational expressions. So let's just say I have the number 25 and I want to divide by 12. And we know that that number is called the divisor. That number is called the dividend. And how do we divide? We want to find a number that we can put up here. Which is the quotient part, so that I get a number less than 25, but the number must be very close to 25. In other words, I need to find the closest multiple of 12 to 25. Well, 12 times 1 is 12, pretty far from 25. But 12 times 2 is very close. I get 24. The next number, 12 times 3, 36, will certainly exceed the 24. Excuse me, the 25. So that's no good. So we always subtract 25 minus 24. I get 1. The term that we have here is what we call the remainder. So you may wonder, why do we have to do long division? Well, the original number 28, the dividend, I called it x, can be written as the product of 12 and 2, the divisor multiplied by the quotient plus the remainder. That's going to work out for us. So 25 would be equal to 12 times 2 plus 1. Notice the remainder is not 0. If the remainder is not 0, it simply means that 25 is not a multiple of 12. That is the simple way of looking at long division with numbers. We use long division for factoring when it comes to rational expressions. What do I mean by that? With rational expressions, if the remainder is 0, then it implies that the dividend is fully factorable. I'm going to start with a very simple case. I'm going to ask the question, can x squared be written in factors of x? The answer is yes. And we know how also, x times x. Long division is a way to get at that. So I look at the degree of the dividend. The degree of the divisor is 1. 1 is less than 2. So I have to multiply the divisor by some number or some variable so that I get x squared. So if I take x and multiply by x, I'm going to get x squared. If I subtract, I'll get 0. So using what I did previously, the dividend is equal to the product of the divisor and quotient plus the remainder. The divisor here is 12. The quotient is 2. Oh, sorry. The divisor here is x. The quotient is x. The remainder is 0. So you can see x squared is now factored as x times x, and it is fully factorable because the remainder is 0. That is in agreement with what we know already, that x squared can be factored as x times x. So one of the important reasons that we do long division is to get factors of the function, if at all possible. We always will get factors of the function, but if it's not fully factorable, we will have a remainder. So here's a simple case where we want to divide 6x raised 4 minus 3x cubed by 3x squared. The degree of the divisor is less than the degree of the dividend, so we can proceed with division. So I have to multiply 3x squared by an expression here so that I get 6x raised 4, or x. In this case, we want 6x raised 4. So if I put 2x squared, 3x squared plus 2x squared is 6x raised 4. Now I'm going to subtract. There is nothing here, so I can put a 0. 6x raised 4 minus 6x raised 4 will get cancelled. Minus 3x squared minus 0 is minus 3x squared. So I've got to come up with a number here so that I get negative 3x squared. So that would be -1. So 3x minus -1, -3x squared. We always subtract. When we subtract, those two will go away. I'll end up having 0. Notice it is the remainder is 0. So the given expression 6x raised 4 minus 3x cubed can be fully factored. So the dividend is divisor times quotient plus remainder. The remainder in this case is 0. So the given expression is fully factorable. So this is actually x squared. So here we have 16a squared plus 64a divided by 4a. So I have to multiply the divisor by some expression so that I get 16a squared. So that would be 4a. Because 4a times 4a is 16a squared. We always subtract, and I'm just going to throw in 0 there. Those two will get cancelled. 64a minus 0 is 64a. So we have to multiply 4a by some number or expression. So I get 64a. 4a multiplied by 16 will give me 64a. We always subtract and we get 0. So the expression 16a squared plus 64a is fully factorable as 4a times 4a plus 16. Here we have x squared plus 3x plus 2, and we want to divide it by x plus 2. So I have to multiply the divisor by some expression so that I get x squared. And mind you, I wrote the polynomial in decreasing powers of x. The divisor must also be in decreasing powers of x. If I put in, before I get to that, since I have x squared, we only care about that first term. So that first term is going to decide as to what number I need here so that I get x squared there. So I am going to multiply by x because x times x will give me x squared. Since I have another term, I'm going to multiply that 2 by x also. Now I subtract. We always subtract. x squared and x squared would go away. 3x minus 2x is x. And since there is nothing below 2, I'll just put 0. 2 minus 0 is 2. I can go one more step because the degree here is equal to degree there. We stop if the degree of the the remainder goes below the degree of the divisor. Well, I need to get an x, so the only way to get that in the quotient is to add 1. So x times 1, x, 2 times 1, 2. We always subtract. The answer is 0. So x squared plus 3x plus 2 is equal to x plus 1 times x plus 2. It is fully factorable. So we have 3x squared plus 19x plus 20 and x plus 5. So we have to multiply by some expression there so that I get 3x squared here. And all I care about is that first term to get that 3x squared. So if I multiply x by 3x, I am going to get 3x squared. Since there is a 5, 5 times 3x is 15x, and then 0. We always subtract. 3x squared would go away. 19x minus 15x is 4x. 20 minus 0 is 20. We have to multiply the first term, x, in the divisor by a number or an expression, so I get 4x. So in this case, that would be 4. 4 times x, 4x. 5 times 4, 20. When we subtract, we get 0. The remainder is 0. So 3x squared plus 9x plus 20 is fully factorable as x plus 5 times 3x plus 4. Consider the cubic polynomial that we have. I cannot factor it just by looking at it. But if I have a hunch that 2x plus 4 might help us in factoring the cubic polynomial, then by doing long division, I can find that factor. And if I get no remainder at all, in the sense that remainder becomes 0, I get 2 good or 3 good perfect factors. So let's say if the given polynomial is factorable. So we are dividing 4x cubed plus 7x squared plus 8x plus 20 by 2x plus 4. I've got to multiply by some expression there so that I get 4x cubed, and I'm going to multiply the expression with the first term of the divisor. So that expression is 2x squared. 2x squared times 2x is 4x cubed. 2x squared times 4 is 8x squared. 0, 0, negative. The 4x cubed will go away. 7x squared minus 8x squared, negative 8x squared. 8x minus 0, 8x. 20 minus 0, 20. So I've got to multiply the first term of the divisor by some expression or number over here so that I get negative x squared. So the number has to be negative, negative 1/2 x. Because if I multiply 2x by negative 1/2 x, I will get negative x squared. So negative x squared, 4 times negative 1/2 is negative 2x. I subtract, we always subtract when it comes to long division. Those two would go away. 8x minus x minus 2x would give me 10x. Plus 0, I'll get 20. So I need to multiply the first term of the divisor by some expression or number here to get 10x. So if I multiply 2x by 5, I'll get 10x. 5 times 4 is 20. We always subtract. Those two would go away. Those two would go away. The remainder is 0. So I am able to write 7x cubed plus 8x, 4x cubed plus 7x squared plus 8x plus 20 as the divisor multiplied by the quotient. There is no way that I could have figured out these two factors without using long division. If it is a second degree polynomial, we can factor by grouping, using a special product, etc. But when it comes to cubic polynomials and higher, things become difficult. Okay. Oops. 8x cubed plus 18x squared plus 16x plus 24. We divide by 4x plus 8. I've got to multiply 4x by some number here or expression so that I get 8x cubed. So 4x times 2x squared will give me 8x cubed plus 8 times 2x squared, 16x squared. The rest are 0. Always subtract. Those two would go away. 18x squared minus 16x squared is 2x squared. 16x minus 0, 16x. 24 minus 0, 24. I've got to multiply 4x in the divisor by some expression here so that I get 2x squared and that has to be 1/2 x. So 1/2 x multiplied by 4x is 2x squared. 1/2 x multiplied by 8 is 4x. Always subtract. Those two would go away. 16x minus 4x is 12x. 24 minus 0 is 24. I've got to multiply 4x in the divisor by some number or expression here so that I get 12x. So 4x multiplied by 3 would give me 12x, and 8 times 3 is 24. If I subtract, I will get 0. So 8x cubed plus 18x squared plus 16x plus 24 is fully factorable as 4x plus 8 multiplied by 2x squared plus x over 2 plus 3. I have a 2 in common in the first factor, so I can pull that out. Actually, I have a 4 in common, so if I pull that out, 4 times x plus 2 times 2x squared plus x over 2 plus 3. There is no way I could have come up with these 3 factors for the given polynomial without knowing the divisor 4x plus 8. Do we have any questions